Okay, let's unpack this. We are diving deep today into a topic that's, well, it's highly specialized, it's strategically critical, and honestly, it's the new bottleneck in high-performance electric racing.
It really is.
We're talking about Formula Student Electric FSE, and specifically the Thermal Management System, or TMS. And we aren't just, reviewing some component choices. We've been approaching this as if we're senior automotive engineering strategy consultants.
That's the frame. We're developing a detailed engineering requirements specification, an SOR, for a new university team.
Exactly. The goal of this deep dive is to help you skip those years of painful trial and error. We want to help you define a world-class competitive thermal architecture right from that very first CAD file.
And for anyone who's new to this, Formula Student Racing, especially at the top tier, think Formula Student Germany, FSG, or FSAE, it has completely shifted. Performance isn't really limited by peak motor power anymore.
Right. That's usually capped at 80 kilowatts by the rules.
It's tapped. The new limit, the fundamental limit, is the TMS's ability to just get heat out of the system and keep all those critical components in their absolute optimum thermal zone.
The sources we've put together for this sort of strategic blueprint, it uses that really rigorous MECE framework. Mutually exclusive, collectively exhaustive.
Which is the hallmark of top-tier consulting and engineering.
Absolutely. It makes sure every single requirement, every potential failure mode is covered.
Yeah.
This isn't just a technical checklist you're getting. This is the strategic pillar that determines reliability. It dictates your car's endurance race completion rate.
And it often defines that all-important efficiency score. When you move from, let's say, hobbyist engineering to world-class competition, the level of detail just explodes. It's exponential.
The sheer volume of precise requirements in this spec is incredible.
Down to the exact type of fluid fitting, the desired thermal conductivity of a potting compound. That's what separates a car that struggles to finish from a car that's fighting for the podium. We're defining a system that is integrated, lightweight, and absolutely reliable when the heat is on.
So let's start there with the strategic imperative. Why has the TMS suddenly become, the single most defining piece of architecture on the car?
The sources define three really clear strategic value propositions. And every competitive team, they have to execute these flawlessly. These three pillars, they govern the entire design philosophy.
Okay, what's the first one?
The first is completely non-negotiable. Absolute compliance. This is the safety and regulatory mandate. You have to ensure all component temperatures, especially the battery cells, stay below both the legal limits set by the rules.
And the physical limits from the manufacturer.
Exactly.
Yeah.
Even in extreme conditions. The rules say you have to design for up to 35 degrees Celsius ambient. If you miss this, if one cell goes over, you're black flagged. You're out. It's that simple.
So that's the baseline. The second pillar, I assume, is where the speed comes from.
This is performance maximization. It's not enough just to finish, You have to use the full potential of your system. And that means precisely controlling the battery cell temperature to keep its internal resistance at its lowest possible point.
Which minimizes that internal voltage drop.
Right. And at the same time, you have to keep the motors and inverters running in their high efficiency zones. If you do that, you can actually deliver the full 80 kilowatt power limit for the whole 22-kilometer endurance event. You won't be forced to decreate halfway through because something is overheating.
And the third pillar. You said it was the most sophisticated.
It is, because it reflects that strategic efficiency-first mindset, system efficiency optimization. Every single pump and every single fan in your TMS is a parasitic drain on your 12V system.
And that ultimately comes from your main high-voltage pack.
Exactly. If your cooling system is poorly designed, if it's running heavy, inefficient pumps at full blast the whole time, you are actively burning energy that should be going to the wheels. So the spec demands minimizing those parasitic electrical losses and, just as important, minimizing the mass of the cooling system itself.
To boost the power-to-weight ratio.
Of course. And all of this, all three of those pillars, they hinge on one single non-negotiable boundary condition.
The 60 degrees Celsius battery limit.
That is the law. And it basically defines your entire TMS technology choice from day one. It is, without a doubt, the hardest constraint in the entire design. We're looking at specific rules here. EV 5.8.3 and 5.8.5, which say the BMS has to monitor at least 30% of your cells.
And absolutely no monitored point can go over 60 degrees Celsius.
Not one. And the implication of that number, 60C, it's just profound for the entire car architecture.
Let's just break down the math on that for a second, because this is where the strategy really pivots.
Right. If the rules say we have to design for a hot day, 35 degrees Celsius ambient, which is common in a European summer race, and your absolute ceiling is 60 C.
You're left with a tiny window.
You're left with a maximum allowable temperature rise, a delta T of only 25 Kelvin, 25 degrees.
And to put that into perspective, 25 Kelvin is, I mean, it's nothing when you're pushing 80 kilowatts through a super high density lithium-ion pack.
That tiny 25 Kelvin window is, like you said earlier, the absolute death knell for simple forced air cooling. You just cannot shed that much heat with air, especially with modern cells, without turning your battery pack into this huge, inefficient air conditioning unit.
It's physically impossible.
It is physically impossible to meet the performance demands and stay in that margin with air. So that immediately forces the strategic requirement. You have to adopt optimized liquid cooling.
Usually through cold plates.
Typically cold plates, or you go to the very high-risk, high-reward solution of dielectric immersion cooling. But for a new team, our spec mandates liquid cooling with cold plates. It's the only rational starting point for robustness and, frankly, simplicity.
And it's not just the temperature. The rules are getting really specific about how you measure it. Rule EV 5.8.14 seems to be looking ahead.
It's a forward-looking constraint, yeah. It suggests future rules might require sensors to directly contact the cell's hotspot, or, even more specifically, the negative terminal tab.
So we have to bake that into the requirement specification now. Why the tab specifically?
It addresses the #1 measurement failure mode, lag. If your sensor is poorly coupled to the cell, maybe it's a bit offset or there's a thick layer of glue, by the time that sensor reads 60 degrees.
The actual cell core is way hotter.
The core could already be at 70 and heading towards thermal runaway. The tab is chosen because it's a fantastic thermal pathway out of the cell. So the mechanical design must have specific mounting slots or use a highly conductive potting compound to ensure you have immediate intimate contact with that tab. That guarantees minimal lag and gives the BMS the maximum time to intervene.
There are also some really critical mechanical constraints, especially for teams using pouch cells. Rule EV 5.5.9 is very strict on this.
And this is something newer teams overlook all the time. It says the pouch cell tabs, those fragile little foil connections, cannot bear any mechanical load, zero.
So your cooling fixture is the aluminum plates holding the cells.
They cannot simply clamp down on the tabs to hold the cell in place.
Yeah.
The fixture has to be, exquisitely designed to securely fix the cell body and then use the tab purely as a thermal extraction point, not a structural one. If you stress those tabs, they will eventually fatigue, crack, and you're looking at a catastrophic internal short.
And then there's the reality of racing. There's always a rain test.
Always. Rules INN 4.2 and EVS 5.1 mandate the car pass a test that simulates wet weather. And the TMS cannot be the system that compromises the car's electrical safety.
Meaning everything has to be waterproof.
Everything. Pumps, fans, and any connection where a fluid line enters or exits the high-voltage battery box must have an ingress protection rating of IP65, ideally IP67. The coolant is often conductive. If a seal fails and water gets in, you have an immediate catastrophic ground fault. Your race is over.
There's one more small detail that often separates the pros from the rookies. Serviceability. Rule EV 5.6 says the battery pack has to be easily removable.
Right, for safety, for maintenance, and this directly impacts your TMS plumbing. Your liquid cooling loop has to incorporate specialized quick disconnects. We're talking professional dry brake connectors.
Okay, wait, why can't a team just use simple ball valves or, some standard industrial quick release fittings? They're way cheaper.
Because standard fittings leak when you disconnect them. They spill. And you cannot, under any circumstances, afford to spill potentially toxic, corrosive, or conductive coolant in your garage or on the track. Dry brake technology means when you separate that connection, internal seals activate instantly, trapping the fluid on both sides with almost zero spillage. This detail isn't negotiable. It's a critical safety and operational requirement.
Okay, here's where the strategy shifts from just following the rules to, fundamental engineering. As consultants, we have to quantify the heat before we can design the defense.
Exactly. We're skipping the guesswork. So the first step, defined in the SOR, is the strategic component choice, the cell. This determines your entire heat load. And the industry standard for high-power formula student is the Molicel P45B, a 21-1800 format cell.
It's a performance beast for sure, but we know that level of performance always means a lot of heat.
Always. So we model a common FSE system. 600 volts, configured as 144 cells in series and 2 in parallel, so 288 cells total. The key number for us, for the thermal calculation, is its DC internal resistance, the DCIR. At about 50% state of charge, it's around 15 milliamps.
15 milliamps. That sounds so tiny, almost negligible.
It sounds tiny, but that invisible resistor inside every single cell is what's generating all your heat. It's the thermal enemy. The heat generation is primarily from what we call irreversible Joule heating.
The I squared R formula.
Current squared times resistance. And because FSC is all about high current peaks, Joule heating just completely dominates the thermal load. We rely on good empirical data for the cell, which shows that under race conditions, about 6% of the total energy you use is converted directly into waste heat.
Okay, let's translate that 6% into actual numbers for the TMS. We have to look at the sustained heat versus the peak heat, right?
Yes. In the 22-kilometer endurance race, the car is pulling an average of, say, 30 to 35 kilowatts for about 40 minutes. At that sustained average power, the total continuous heat generation in the pack is about 2.04 kilowatts.
2 kilowatts continuously.
Continuously. And when you divide that across our 288 cells, that is a relentless load of about 7.1 watts of heat from every single cell for the entire race.
7.1 watts. Again, it doesn't sound like much, but multiply that by 288 cells all packed tightly together, and you have a recipe for a thermal catastrophe.
And that's just the average. Now look at peak acceleration. Launching, corner exit. The driver demands the full 80 kilowatts. The sources show the peak heat generation spikes to about 4.8 kilowatts.
Which per cell is?
A massive 16.7 watts of heat per cell, even if it's just for a few seconds.
So if the peak is almost 17 watts, why do we focus on that 7.1 watt continuous load as the sort of system killer when we're sizing the radiator and the pump?
Ah, that is the core strategic insight. The peak load is high, yes, but the system has thermal inertia. It takes time for that heat to build up and get to the coolant. The 7.1 watts, however, that's continuous. Our CFD simulations are emphatic on this point. 7.1 watts of continuous heat from one cell will push its temperature past that 60-degree red line in minutes if your liquid cooling isn't perfect.
So the continuous load dictates the system's baseline size and sustainability.
And the peak load dictates how fast your control system needs to react.
We can't forget the rest of the powertrain either. The motor dumps a huge amount of heat into the system. Let's say a common choice, an MREX 228.
Right, and even though these motors have peak efficiencies up around 96% under max 80 kilowatt output in a real race, well, you're operating outside the optimal RPM range, you're using field weakening, temperatures are high. You have to conservatively model the overall system efficiency at maybe 92%.
Wait, 92% still sounds pretty good. Why is the SOR being so conservative? Is that just padding the heat load?
We have to be. If we design for 96%, we are designing for failure. That 8% inefficiency translates directly into a peak heat loss of 6.4 kilowatts from the motor alone. That heat has to go somewhere.
Or you violate the physical constraints of the motor itself.
The non-negotiable one. The permanent magnets have to stay below 100 degrees Celsius. If they go over, you get irreversible demagnetization. The motor's torque output is permanently degraded. The winding limit is a bit higher, usually 120C, but the magnets are the hard stop.
And then there's the inverter, the power electronics. Using modern silicon carbide, a Cascadia PM100DX or something similar.
6-stack is incredibly efficient, 97–98%, so the peak loss is lower, about 1.6 kilowatts. But the challenge isn't the total volume of heat, it's the concentration.
The heat flux density.
Exactly. 6 chips are tiny, so you have a massive amount of heat packed into this microscopic area. It's like trying to cool a tiny super hot laser beam instead of a large oven.
And that's a great analogy.
So while the CC junction temperature, the TJ, can technically handle up to 175C, the absolute limit is the stuff around it. Specifically, the critical DC link capacitors and the control boards. They restrict the coolant inlet temperature to less than 60C. If the fluid going into the inverter is too hot, those surrounding components will fail. And this is precisely why a single loop just cannot work.
Which brings us squarely to the architectural mandate. You have two sets of components with fundamentally conflicting needs. The battery needs to live in a cool zone, under 55C, while the motor and inverter are happy and even more efficient, running at 70 or 80C.
So a single loop can't serve both masters. Therefore, the mandatory strategy in the SOR is the parallel dual-loop architecture. You physically and hydrodynamically isolate the two thermal worlds. You have a low-temperature loop, the LTL, just for the battery.
And a high-temperature loop, HTL, for the powertrain.
Correct, for the motor and inverter.
Let's start with the LTL, the low temp loop. That's the one with the tighter tolerance.
Yeah.
What's the target inlet temperature for the battery coolant?
For the LTL, the inlet temp has to be aggressive. We're talking 30 to 35 degrees Celsius. That gives you the necessary margin against that 60-degree ceiling, and just as important, it keeps the cells in their thermal sweet spot.
Where the internal resistance is lowest.
Exactly, which boosts your overall system efficiency. Now, within that LTL, there's a critical technology choice. Option B, the baseline, or option A, the advanced one. We defined option B as cold plate liquid cooling.
And that's the recommended baseline.
It is, because it's mature, it's reliable, and it uses standard water glycol, which has an excellent specific heat capacity. It's great at pulling heat. The mechanism is custom-machined aluminum serpentine tubes that clamp against the sides of the cells.
But if you have an aluminum plate right up against a high-voltage cell, you need insulation. But that insulation can't block the heat transfer. This is where the thermal interface material, the TIM, comes in.
The TIM is the efficiency bottleneck of the entire cold plate system. It's that thin layer between the cell and the plate. The SRR mandates a high conductivity TIM, ideally between 3 and 10 watts per meter Kelvin. But here's the critical safety part. It must also have a robust dielectric strength. We specify greater than or equal to 6 kilovolts per millimeter. It has to move heat brilliantly while also preventing a high voltage short circuit.
Okay, now let's talk about option A, the advanced high-risk choice, dielectric fluid immersion cooling. If the goal is max performance, why isn't this the first choice for everyone?
Because while immersion cooling offers phenomenal thermal performance, the integration is a nightmare for a new team.
What are the pros? Why even consider it?
The main pro is extreme temperature uniformity. You can get a cell-to-cell temperature difference of less than 2 degrees Celsius across the entire pack. It's incredible. And it also gives you unparalleled thermal runaway suppression. If one cell fails, the fluid absorbs and spreads the heat so fast it prevents propagation. It's like fireproofing your battery.
But the strategy consultants said no for a new team. The cons must be huge.
They are massive. The fluid is dense, so it adds a lot of weight. The sealing requirements are astronomically complex. You're sealing a whole tub of liquid, not just a few tubes. And most critically, the fluid can interfere with the insulation monitoring device, the IMD, which is a critical safety system.
So the risk of getting it wrong is just too high?
The technical risk of integration failure far outweighs the thermal benefits for any team still developing its core architecture. So we mandate option B.
Okay, switching to the HTL, the high temp loop for the motor and inverter. We can tolerate a higher inlet temp here, maybe 45 to 60 C.
Right, and the crucial architectural decision here is the configuration logic. The components are in series, but the order is non-negotiable. It has to be pump, then inverter, then motor, then radiator.
Why that specific order? Why does the inverter get the coolest fluid first, even though the motor generates way more heat?
It comes down to those absolute constraints. The inverter, with its semiconductors and capacitors, has the lower, harder temperature limit, that 60 C limit on adjacent components. The motor, with its 100 C magnet limit, has a much higher thermal tolerance, so we prioritize the most sensitive component. The motor gets slightly warmed fluid, but it can still easily shed its 6.4 kilowatts before the coolant heads off to the radiator.
Let's talk about the hydrodynamic specs, the flow rates. What kind of movement do we need in these loops?
The LTL for the battery has those winding serpentine channels, which create high flow restriction. So we want a modest flow rate, 3 to 6 liters per minute, to give the fluid enough time to absorb heat. But we aim for a low pressure drop, under half a bar, to keep the pump's workload down.
And the HDL, dealing with over 6 kilowatts of heat, has to be different.
It's a powerhouse loop. The HTL needs a much higher flow rate, 8 to 12 LPM, with a slightly higher allowable pressure drop up to maybe 0.8 bar. The standard fluid is a 50-50 mix of water and ethylene glycol for antifreeze and anti-corrosion.
But we should address a subtle but really important strategic choice here about the fluid itself. Standard water glycol is conductive.
It is. A very smart consideration for advanced teams is to specify low conductivity coolants, aiming for less than 100 microsiemens per centimeter. It costs more, and you have to manage it carefully, but it drastically reduces the short circuit risk if a hose leaks near a high voltage terminal. The SRR suggests this as a mandatory risk reduction feature for a top-tier pack.
Okay, so when we move from architecture to actually picking the components, the guiding principle is this weight-performance reliability trade-off.
It is so tempting for student teams to just buy cheap components with big numbers on the box, but they will fail under the vibration, the pressure, the thermal cycling of a race weekend. Reliability has to be paramount.
Let's start with the heart of the system, the electric water pumps, the EWPs. What are the engineering requirements beyond just moving fluid?
They have to be 12V DC, they must be IP67 rated, they have to be lightweight, and critically, they must have PWM pulse width modulation speed control capability. PWM is non-negotiable because it lets the control system dynamically adjust pump speed, which drastically reduces your 12V power draw when cooling demand is low.
I see a lot of teams using common aftermarket pumps like the Davies-Craig series. What's the strategic advice there?
Well, those pumps are functional, but they're often a compromise. The EWP 150, for instance, can be heavy, over a kilogram, and it sometimes lacks the precise control interfaces you need for an advanced system. Our preference is for OEM-grade reliability. We strategically recommend something like the Pierburg CWA series, which you'll find in high-end BMWs. They have exceptional reliability and really precise control.
And if weight is the absolute #1 concern.
Then you look at specialized racing alternatives like SPAL brushless pumps. They're incredibly efficient, often under half a kilo, and they have integrated PWM or CAN interfaces. They're perfect for a lightweight, high-performance car where every gram and every watt of 12V power counts.
Next up, the heat exchangers, the radiators. Space is always a premium in the side pods, so you need max performance per square inch.
We issue an immediate ban on using, traditional heavy copper brass units or just grabbing some off-the-shelf car radiator. We require high-performance, custom-made aluminum brazed cores. These offer far superior heat transfer and pressure tolerance.
And you mentioned the internal structure is really important too.
Oh, yes. The tube specification has to be advanced. Microchannel extruded tubes or rolled tubes. They handle higher pressures and give you a much better in-tunnel surface area for heat exchange.
Let's talk about a crucial failure mode you see all the time, mid-endurance, debris clogging the radiator.
It's a guaranteed problem. So we must limit the fin density to between 18 and 22 fins per inch, or FPI. Teams think a denser fin pack means more cooling, but anything denser than 22 FPI will clog up with rubber debris and track fallout.
I can just picture it.
I saw a team once run a 30 FPI radiator. Halfway through the endurance run, it looked like the car was wearing a thick black velvet scarf. They lost 40% of their cooling capacity and had to retire. 18 to 22 FPI is the optimal trade-off.
A radiator is useless without good airflow, so aerodynamic integration is key.
The SOR mandates the radiator be side pod mounted and sealed with a custom carbon fiber duct. That duct has to ensure 100% of the airflow goes through the core, not around it. You need CFD analysis to guide the geometry here. A key output from that CFD must be the pressure balance, which usually shows the side pod intake should be about 80% of the radiator's frontal area.
Now for the cooling fans, which are critical for low-speed sections. This is another area where cheaping out can lead to disaster.
We have to issue an absolute prohibition against using consumer-grade PC cooling fans. I don't care how good their specs look online. They are designed for clean, climate-controlled rooms. They have zero tolerance for vehicle vibration, debris impact, and water. They will fail catastrophically during the rain test or on the track.
So what's the vehicle-grade replacement?
You must specify SPL Automotive fans. They're VA series brushless axial fans. They have IP68, IP6K9K protection, a life expectancy over 20,000 hours, and mandatory PWM control. It's a foundational reliability mandate. Only use components designed for the harsh automotive environment.
And finally, the plumbing and connections, which are all governed by a zero leakage policy.
Leakage is a severity 10 failure in our FMEA, so we need aviation or motorsports grade connections. For flexible lines, we recommend Wiggins or HydroFlow clamshell connectors. They're lightweight and robust against vibration. For the required battery quick disconnects, the mandate is Jiffy-Tight dry brake connectors. Anything else is a risk.
And the tubing material itself. Lots of teams use silicone hoses everywhere. Is there a smarter choice?
Silicone is essential for short, vibration-dampening connections, like near the pump. But for the long, straight runs from the rear powertrain to the side pods, teams should strategically use aluminum hardlines. They're lighter than thick hoses, more durable, and critically, they don't expand under pressure. That expansion in soft hoses actually absorbs energy and can destabilize the system pressure. Hardlines are just better.
Okay, so we've defined the hardware and the architecture. That gives us the potential. But the software, the control strategy, is what actually turns 16.7 watts of peak heat into a controlled, efficient system.
This is where we move the TMS from a simple on-off thermostat into an intelligent, efficiency-optimizing system. And the first step is the sensor fusion strategy. You need highly accurate, low-latency data.
So for the battery, that means at least one sensor per parallel group.
At least one NTC sensor per parallel group positioned right at the hotspot with that excellent thermal coupling we talked about earlier.
And for the fluid itself, how do we know if the cooling is actually working?
We need temperature sensors at both the LTL and HTL inlets and outlets. This setup lets the system do a real-time heat exchange calculation. Heat flow equals mass flow rate times specific heat times the temperature difference. This gives the control unit precise feedback on how much heat the radiator is actually shedding.
What about flow meters and pressure sensors? They seem crucial for that calculation, but they add weight.
They are strategically important, but only during development. We mandate their installation during dyno and bench testing to accurately characterize the pump curves against the system resistance. Once you have that essential data, you take them off for the race. The control system then just estimates the flow based on the pump's current draw and RPM. You save crucial weight while keeping high fidelity control.
It's clear that traditional bang-bang or simple PID controls are just not good enough for this. The strategic recommendation is Model Predictive Control, or MPC.
MPC is the required next-generation strategy. Traditional control is reactive. It sees the temperature as 58 degrees and then it ramps up the fans. MPC is proactive. It operates on the future.
How does it predict the future cooling demand?
It uses the car's validated thermal models of the battery and motor, and it combines that with real-time data from the vehicle control unit, things like GPS, throttle position, braking intent, to predict the future temperature trajectory a few minutes in advance. It's like having a thermal weather forecast for the next 2 laps.
Give us a specific example of how that intelligence can save a race.
The best use case is pre-cooling. Imagine the car is flying down the back, straight at full speed. The VCU predicts that in 15 seconds, the driver is going to lift off and hit the brakes hard for a hairpin. That's a huge regen event, a massive spike of heat into the battery.
Okay.
Instead of waiting for that heat spike to hit the cells, the MPC controller preemptively ramps the pumps and fans to full speed before the braking event even starts.
So it's leveraging the system's thermal inertia.
Exactly. It uses the thermal mass of the coolant to pull down the baseline temperature, effectively opening up headroom for that predicted heat spike. By the time the battery is seeing that maximum heat from regen, the cooling system is already at max capacity, keeping everything stable.
And the efficiency benefit must be huge.
Oh, it transforms the cooling system from an energy hog into an efficiency optimizer. During slow sections or behind a safety car, MPC can dynamically reduce pump and fan speeds to the absolute minimum required. Studies show this can save up to 60% of the cooling system's electrical energy compared to a traditional system that just runs everything at 75% just in case.
Beyond the control software, integration is key, and the SOR pushes heavily for additive manufacturing, or 3D printing.
3D printing is a game changer here. For fluid distribution, we strongly recommend using SLS or SLA printing with robust materials like high-temp nylon. This lets teams create incredibly complex integrated fluid manifolds.
And why is a 3D printed manifold so much better than just a bunch of standard fittings and hoses?
Because it eliminates joints. Every single joint, every hose clamp, every fitting is a potential leak path. And we know leakage is a severity 10 failure. By consolidating 10 separate fittings into one complex 3D printed part, you slash the leakage risk, and it saves weight and assembly time.
And this integration also extends to structural fusion.
Yes. The very best teams don't just bolt on their cold plates. They design the cooling jackets to also act as structural support members for the battery modules or the motor casing. This is done with specialized high-strength, high-conductivity aluminum alloys using direct metal laser sintering, DMLS. You get incredible performance and you save chassis weight.
Let's touch on one small but really consequential detail: air management. You identified airlock as one of the highest priority failure modes.
It scored a risk priority number of 210 in our analysis, which is huge. It means it's likely to happen, it's hard to detect, and the impact is severe. An air bubble trapped in a cold plate or a motor jacket will stop the fluid flow right there.
And you get immediate localized overheating.
And component failure. So the SR mandates easily accessible fill ports and bleed ports. Crucially, the system's absolute highest point must have a bleeder valve. And we mandate the use of vacuum filling procedures. You don't just pour coolant in. You have to pull a vacuum on the whole system first, then introduce the coolant. That ensures the fluid gets everywhere and eliminates 100% of the air.
Okay, we've designed it. Now we have to validate it. A world-class team relies on data and simulation, all structured by a DVP&R.
The design verification plan and report, yes. We validate the maturity of the system before it ever touches the track. And that starts in the virtual world with the virtual validation chain.
Moving from low fidelity to high fidelity.
First is the 1D system simulation, using something like MATLAB Simulink or GT Suite. This models the entire vehicle's energy balance. We input the full 22-kilometer endurance drive cycle data to confirm that our radiator sizing and pump selection are mathematically sufficient to stay below that 60-degree limit. If the 1D model fails, the design is scrapped.
Next, we move into 3D with computational fluid dynamics, CFD.
CFD is essential. We use solvers like ANSYS Fluent to focus on two areas. First, the battery pack's internal flow field. We have to optimize the design to ensure perfect flow uniformity among all 288 cells to eliminate any dead zones.
If the flow isn't uniform, you get one cold side of the pack and one hot side.
Exactly. And you're only using the performance of half your pack. The second use for CFD is optimizing the external side pod ducting to guarantee maximum effective airflow through the radiator core.
And finally, we have to verify the mechanical resilience of all these custom parts with finite element analysis, FEA.
These cooling systems undergo brutal thermal cycling, from a cold garage up to 80 degrees operating temp and back down, hundreds of times. FEA performs thermal stress analysis on our 3D printed manifolds and interfaces to verify that this constant fatigue won't cause them to crack or develop microleaks.
Once it's mature virtually, we move to the physical testing milestones. What's the very first test?
The leak test. The system is held at 1.5 times its max operating pressure for at least 30 minutes. The pressure decay has to be less than 5%. If it fails, you fix it. A small weep on the bench is a race-ending failure on track.
And then component verification on the bench.
Right. We use a fluid test stand to calibrate the actual system resistance curve against the pump's PQ curve. This confirms the pump is operating in its highest efficiency zone. We also conduct thermal shock tests following ISO standards to prove the durability of all our custom parts.
The last step is translating all that lab data to real-world performance.
You have to perform a mock rain test in the workshop to ensure those IP-rated fans and pumps work perfectly when soaked. And most importantly, you rely on telemetry during track testing. We monitor max cell temp, motor temp, inverter temp, and the parasitic power draw of the pump and fan. That telemetry is the critical feedback loop you use to refine and finalize your MPC parameters.
So we have to have a robust failure mode and effects analysis, a DFMEA, to address the biggest risks. Let's start with coolant leakage.
Coolant leakage is a severity 10. It leads to immediate loss of power, potential short circuit, total race retirement. The mitigation requires redundancy. Using those aviation-grade fittings, designing leak catch channels into the battery box, and installing a critical safeguard. A moisture sensor at the bottom of the box that triggers an immediate alert.
The highest risk priority number was for airlock. Why is that one so hard to detect?
It's an RPN of 210 because it's highly probable and very difficult to detect without dedicated sensors. The only true mitigation is in the design. Mandatory bleeder valves, the vacuum fill process, and monitoring the pump's behavior for anomalies.
And what if the pump itself just fails mid-race?
Pump failure is a high severity, an 8. The mitigation is a software-based early warning system. The control system must continuously monitor the temperature rise slope, the DTDT. If the pump fails, the temperature will start rising at an accelerated rate. That rapid rise immediately triggers a subtle proportional power derating of the vehicle.
Which leads us to the strategic concept of dynamic derating. Why is a subtle proportional derate better than just shutting the car down?
Because a hard shutdown is 0 points for the endurance event. A proportional derate, maybe it cuts peak power from 80 kilowatts to 60 or dials back regen. It ensures the car can still finish wounded. It prioritizes race completion over peak power, salvaging crucial competition points.
And finally, integrating pre-race strategy. It's not just about managing heat during the race, but managing thermal capacity before it even starts.
We focus on maximizing the thermal buffer. Before the event, the team must use external chillers, or if the rules allow, things like dry ice on the radiator core to drop the battery starting temperature down to maybe 20 degrees Celsius. This gives you a critical 15 Kelvin buffer against the ambient temperature, giving the MPC controller maximum time before any heat stress occurs. It's pure strategic competitive advantage.
Okay, let's zoom out. This entire deep dive, this engineering requirements specification, has shown that the thermal management system isn't a peripheral subsystem anymore. It is the core strategic architecture that defines the success of a modern Formula Student electric car.
It is the single most defining factor of modern FSE performance. If you are developing your next car, you have to internalize these 4 key takeaways.
First, embrace liquid cooling. That 60-degree limit, combined with the power of modern cells, mandates cold plate liquid cooling and a dual-loop architecture. Stop wasting time modeling or testing air cooling. That battle is over.
Second, data-driven decisions. Every major hardware selection, from the radiator fin density to the pump flow rate, must be validated first by 1D thermal modeling and 3D CFD simulation. If you can't prove the math, the part does not go on the car.
Third, details determine victory. Success hinges on flawless execution of the smallest details. We're talking zero-leak, jiffy-tight connections, specifying high static pressure spall fans, and rigorous air management through vacuum filling. A tiny air bubble will ruin your day long before you run out of horsepower.
And finally, smart control. You must adopt Model Predictive Control. MPC transforms the TMS from a crude reactive system into a sophisticated proactive efficiency tool that uses thermal prediction to maximize available power and therefore speed throughout the entire event. Which, it raises an important question for future development. While we focused on minimizing energy loss with these detailed, fixed thermal models, how much more performance could a team unlock if the TMS used advanced machine learning?
If it could update its own internal model during the race?
Exactly. Adapting in real time to subtle changes in battery degradation or track conditions or unexpected weather shifts. Moving from pre-programmed prediction to true adaptive real-time optimization, that's the challenge for your next deep dive.
That concept, an adaptive TMS that learns as it races, that is the definition of the next frontier. You've given us the perfect blueprint to get to the front of the grid now. Thank you for this deep dive into the 60-degree red line. We'll see you next time for more deep dive analysis.